Hi, in this video, we're going to talk about another type of network model, which is the shortest path model. And the shortest path model, the reason why we use this particular type of setup is that it helps us find how a person or an item can travel between one location to another location through a network, at the same time minimizing the total distance traveled. So the most commonly used application of this particular type of model is your Google Maps, which helps you determine what route you should take in order to start at one particular node, let's say node A, and reach your destination at node B. So the roads that you have to follow so that your distance is minimized while you get to your destination is where we're going to use a shortest path model. So again, with like all other network models, we're going to use an example to help us demonstrate how to construct and solve for this type of model. The example that we're using is for a company called Ray Design Incorporated. So Ray Design Incorporated must transport beds, chairs, and all of the other furniture items from its factory to the warehouse, and they have to do this every day. This involves going through several cities. Each city can be thought of it as a node. Ray would like to find the path with the shortest distance in miles. The road network for any shortest path model will be given to you in the form that you see on the slide here. So it's sort of like a very simplified map. And the numbers that you see on each arc here, that gives you the distance between 1 and 2. So needless to say, this is not a 2-scale diagram because all these lines are almost the same length, but the distance that they represent is different. The reason why they're the same length is just to simplify the diagram in the way it looks. The shortest path model is also another example of a network model that has a unique starting point, which in this case is the factory where the products and goods are created. And it also has a unique destination node or ending node. In this case, that destination node is the warehouse. If you remember, this was also the case in the maximal flow diagrams or the maximal flow models, where we assume that we have a unique origin node and a unique destination node. There are no multiple origin nodes or multiple destination nodes. If we assume that there is a supply of 1 unit at the factory and a demand of 1 unit at the warehouse, the shortest path model for Ray Design's example is identical to a transshipment model with a single origin node, a single destination node, and all these other remaining 4 nodes serving as transshipment nodes. So the way you're going to think about it is, in this case, we're not concerned about how many furniture items travel from node 1 to 6, which we generally do in a transshipment or a transportation model. In this case, we're only interested in if a truck starts at the factory and wants to reach the warehouse, which of these routes should it take? So essentially, there's only one truck that needs to leave node 1, and that same truck has to arrive the warehouse at node 6. So our capacity and our requirement is just 1, because we need that one truck to leave the factory and reach node 6 at the warehouse. What the model is solving for is which of these routes is going to be the shortest distance-wise. So we're not, in this case, we're not concerned with how many products or items are loaded in the truck. We're just interested in that one truck itself. Now, because of this reasoning, the supply and demand both equal to 1 unit, which is a whole number. The solution to the model will also have integer valued flows on each arc. By integer, I mean whole numbers again. Hence, the supply of 1 unit at node 1 will flow in its entirety to either node 1 to node 2, or from node 1 to node 3. From there on, it can decide whether to go to node 2 or node 5, and the same way. So this helps us define our decision variables as the flow on road from node I to node J. Again, we're using the general form xij, and the solution value will equal to 1 if that particular road is selected as a part of our optimal solution, and it will automatically be 0 if it's not selected for a route to be taken. So now for this slide, I want you to ignore the bottom half of the slide because that's not what we have discussed so far. I only want you to focus on this top portion where we come up with the objective function. So here, because our objective is to minimize the total distance that is covered between node 1 and 6, we're going to use the distances on each arc or path to help us determine what the total distance traveled will be. So because if I go back to my network diagram here, node 1 to 2, the distance is 100 miles. Then if this route is taken, it will add 100 miles to total distance traveled, which is how we get this 100 times x12. What you also need to remember here is because this is now distance, and distance does not matter if the road is unidirectional or bidirectional, the distance will always remain the same. So the same 100 is going to be used for the way back, which is x21. Now, whether or not that road exists, we'll figure that out in our Excel model, the way we did for maximal flows, where we only highlighted certain cells as yellow and left the remaining ones as blank or set them to 0 because they were not defined in our model. We're going to take the same approach when we get to the Excel solution portion of this particular example. So using the distances in the network diagram, we're going to come up with our objective function, which is to minimize the total distance that is traveled in order to start at node 1 and end at node 2. So now that we have defined our objective function and our decision variables, let's use the net flow equations to help us come up with a constraint equation for each of the 6 nodes that we have in our model, or for this particular example for Ray Incorporated. So I'm going to start off with node 1 first. That's why I put N1 here. And again, the net flow equations can be determined using this formula. Inflow minus outflow is equal to the net flow. Now, let's take the first node. If you look at the first node in our network diagram, which is given to you as a part of the example, you will see that node 1 in this case acts like a pure supply node, which means that there is no inflow into node 1. The truck only leaves node 1, it doesn't arrive back into node 1. So the inflow for node 1 is equal to 0, and the outflow from node 1 is either to take the road that leads to node 2 or take the road that leads to node 3. So the outflow options are x12 plus x13. There are no other roads here, and because this is a pure supply node, the right hand side for this equation, since there's only one truck that we're concerned for, is going to be 1, and again pure supply, which is why we force it to be negative, And if I expand this by opening the bracket, I can cancel these negative signs, and this is simplified to x12 plus x13 has to be equal to 1. And this actually makes sense because we've already said that these x's will take 0, 1 values. So if x12 is 1, x13 has to be forced to be 0 because you cannot take both the routes. You have to take one of the routes. You have to choose. So with the help of this equation, what we're telling Excel is that only one of these two routes can be taken, which is correct. So let's move on to another node. For this one, I'll pick out a transshipment node so that we can learn how to write out the constraint equation for a transshipment node. Okay, so let's pick another node, and this time I'm picking out a transshipment node, and I'll write down the net flow equation for node number 2. Again, just to help me, I like putting down inflow minus outflow is equal to the net flow. Please excuse my handwriting. With the stylus, it's very hard to have a neat handwriting on the screen. So let's determine what the inflow for node 2 is. We said earlier that for a shortest path model, we're assuming that the origin node is a pure supply node and the destination node is a pure demand node. So all the other nodes in between, from 2 to 5, are going to serve as transshipment nodes. And about transshipment nodes, what we know is that they're temporary states. You cannot stay in a transshipment node forever like you can at a factory or a warehouse. So instead, we have to force the net flow to be equal to 0, because all the product, or if there's a car coming in to that transshipment node, it also has to leave the transshipment node. So it's a temporary sort of node. So let's get the inflow into node 2. Looking at the network diagram, you'll see that the inflow into node 2 is from node 1. There's also an inflow from node 3, 5, as well as node 4. So the inflow into node 2 is given by x12, the road from 1 to 2, x32, the road from node 3 to node 2, x42, and x52. This is only the inflow portion of the equation that we're looking at so far. Now let's take a look at the outflow. Again, you're going to go back to the network diagram and see which nodes are connected to node 2. Now, what common sense says is that because we're concerned with distance here and not capacity, the same 4 nodes would be there. But remember that our objective is to go to node 6, reach node 6, start at node 1 and reach node 6. So it doesn't make sense to go backwards, which means that for the outflow, we can drop x21 because we will never go to 21. It's not a route that we will take. We won't go backwards and then go forward. So for the outflow, it'll just be x2 to 3, x2 to 4, and x2 to 5. Oops. So that basically completes the right-hand side of our equation, and the left-hand side of our equation. And for the right-hand side, because it's a transshipment node, we set that equal to 0. And now we can write down our full equation for node 2, which would be what's represented here in this case. So inflow minus outflow is equal to 0. And like I said, since we are not going to be going backwards, it's safe to drop this x to 1 from our model. I mean, it's not going to change your solution really, because Excel would automatically switch this to 0. But just to simplify your model and not have so many variables in there, you can eliminate it without having it affect your final solution. So in the same way, using the same logic, you can come up with the net flow equations for the remaining 4 nodes. 3 of them are transshipment, so we force the right hand side to be equal to 0, and one of them is a pure demand node, so we force it to be equal to 1 because of that one truck that we are studying for the purpose of this particular model. Now we have everything ready to move to Excel. So when it comes to Excel, we've been using the same template for all the models throughout and all the examples, and I have created that blank template that you see in front here. We're going to fill it out with color codings and with functions and formulas in there to help us get the solution in Solver. We know that for our decision variables, those are going to be represented in this box here, but not all of these cells are defined for our model, because if you look at the network diagram, you can go from node 1 to node 2 and node 3, but you cannot go to node 4, 5, and 6. So in that case, node 1 to 1 would just be 0, so I'll force this to 0, and throughout, the diagonal, all of it is going to be 0, because it doesn't make sense to have decision variables to start at A and end at A as well. So that's why the whole diagonal part of this model is 0. Node 1 to 2 and node 1 to 3 are actual roads that exist, so they will be a part of our decision variables, so I'll highlight them in yellow. Whereas node 4, 5, and 6, there is no road that connects node 1 to any of these 3 nodes. So again, I'll force these to be equal to 0. You can even leave them blank, but just don't highlight them so that you're not confused as to which ones are actual roads and which ones are not. The same way for node 2, because we won't really be going from node 2 to node 1, it doesn't make sense to go backwards. I'll force this to be 0 as well. And then from node 2, you can travel to node 3, 4, and 5. So these 3 cells would be yellow. And you can't go directly to node 6, so this automatically, I'll set it to 0. Now, the reason why I'm doing these yellow highlighting only for certain cells is it doesn't really affect your solution, but it makes reading the solution and interpreting it really easy, because only the cells that are in yellow, you know that Solver got a solution for those cells, and the remaining ones are 0. So even if some of these yellow cells are 0, you know that it's because Solver didn't select those roads, not because it didn't exist. So the color coding helps you identify which roads actually exist and have not been selected, as opposed to roads that don't exist and have 0 values in them. So from node 3, again, you're probably not going to go backwards, so you can set those to 0. And from 3, there is a road that connects 3 to 2 and 3 to 5, but because we're not going backwards, you'll only consider the road that goes to 5 as a decision variable. So I'll highlight that in yellow, and the other roads become 0. And following the same approach, you can fill out this decision variable box with yellow highlights and zeros. Okay, so now I have completed the decision variables box in my Excel template. It's time to fill out the flow out and flow in numbers using sum functions. So I'll do that. This is similar to what we've been doing in all the other transportation problems. in would simply be the sum of that whole column, and drag it across. Now, because there are functions in these cells, I have to put a color coding of blue in here to help me remember. And then the balanced flow equation would simply be the flow in, which are given in these cells here down in the flow in row. Okay, and the flow out are these cells in one single column, so I can drag these down without formatting. The net flow is simply equal to inflow minus the outflow, and drag it down. The reason why I'm doing this really quickly is because we've done this multiple times, so I don't want to waste your time. And because all these cells have formulas in there, so I'll highlight them in blue. For node 1 and node 6, if you want to be specific about it, because these are pure supply and pure demand nodes, we know that node 1 would have no inflow into it, and as you can see, even here the whole column is set to 0 and there are no yellow cells here, so this won't change after we get the solution. So we can remove the blue highlight for this particular cell. And for node 6, we know that once it reaches this destination node, it's not going to leave, for the sake of this particular model. So that 0 also will probably not change, and we can just change it to a simple 0, or we can use the cell reference that we added in there. It's not going to change because these zeros here and these numbers here. So now we're going to add the sign as well as the right hand side values for these net flow equations. We know that for the first node, which is node number 1, and that's our origin node, we force it to be -1. The remaining 4 nodes are transshipment nodes, so we force it to be equal to 0, and finally for the demand node, we force it to be equal to +1. And the distances are here calculated inputted in this second box right underneath our decision variables, and the shortest distance would be a sum product of our decision variables with these distances box here, and this will also serve as our objective function. So I'll put a green color code here, and we need to minimize this so that I can remember that in Solver. So actually, when we go to the Solver window for this particular example, C2 would be the cell where we set our objective function. We need to minimize that, and then we put down the changing variable cells in here. You'll notice that I didn't add the changing variables as one single block, like I've been doing for other examples. The reason for that is because this is a minimization problem, and the distances that we added in our second box for the roads that don't exist is equal to 0, and Excel doesn't know that we have to get to our destination node, so it might still use the nodes which are not the roads which are not defined as a part of the changing variables if we select the whole box. So which is why I've added only the yellow cells in here to help me get the solution. And when I click solve, the solution is 290. That's the shortest distance that you can travel by selecting roads from node 1 to 2, then from node 2 to go to node 3, from node 3 to go to node 5, and then eventually from node 5 to go to node 6. And that's going to be the shortest distance that you can cover in order to travel from node 1 to node 6.